The title of this presentation is Local Climate Zones Classification. Local climate zones are defined as areas with uniform surface cover, structure, material, and human activities, with a minimum radius of 200 to 500 meters, which exhibit local-scale climatic nature. Until recently, there was no universal approach to describe and characterize the physical nature of cities for urban climatologists. Much of the existing terminology was not transferable across cultural and geographical regions. To address this problem and to help standardize methods of observation and documentations in urban heat island studies, Stewart and Oke developed the Local Climate Zone Classification Scheme in a 2012 paper. The scheme comprises 17 zones based mainly on properties of surface structure, such as building and tree height and density, and surface cover, that is pervious versus impervious. Each zone is local in scale, meaning it represents horizontal distances of hundreds of meters to several kilometers. The concept of local climate zones can be found in the papers of Stewart and Oke in 2012. The paper comes with a toolbox at www.woodept.org. The Local Climate Zone Generator is a web-based application to create local climate zone maps. The application is described in the Demercery 2021 paper. After this presentation, you will prepare a local climate zone map for practical too. During last presentation, we have covered the topic of urban heat island, and we can use the land surface temperature derived from satellite imagery to monitor urban heat island. We also discussed some factors contributing to the formation of urban heat islands and how to mitigate with urban planning. In this slide, the table extracted from Oke's 1982 paper describes how urban modification to the surface energy and radiation balance has contributed to the formation of urban heat islands. First, it is due to greater absorption of solar radiation caused by multiple refraction and radiation trapped by buildings' wall and vertical surface in the city. Second, taller and more compact buildings have led to greater retention of infrared radiation in street canyons due to restricted view of the radiatively cold sky hemisphere. Third, there is a greater uptake and delayed release of heat by buildings and paved surfaces. This is not only because of the properties of building materials. It is also due to the fact airflow is retarded at canopy layer, which has reduced convective losses and formed a solar and infrared radiation trap. Fourth, the replacement of moist soil and plant with paved and waterproofed surfaces has caused a decline in surface evaporation. The result is a greater portion of absorbed solar radiation at the surface being converted to sensible heat rather than latent heat. Fifth, there is a greater release of sensible heat and latent heat from the combustion of fuels in transportation, industrial processing, and domestic heating and cooling. Following the analysis of the factors contributing to the urban heat island, it is understood that not only land cover is an important indicator. Urban morphology has to be considered to understand better the urban heat island effect. Urban morphology refers to the study of the formation of human settlement, that is the urban form. It represents the structure and shape of a city, including streets, squares including the public space, street blocks, plots, and buildings. The local climate zone system is a universal classification mechanism for urban and natural landscapes. It plays an increasingly important role in urban climate research. Following the classification scheme in Stewart and Oke's 2012 paper, there are 10 build types and 7 conventional land surface classes. The 10 classes of build types include 3 classes for compact or dense developments of high-rise, compact mid-rise and compact low-rise. There are 3 classes for open or more dispersed arrangement for high-rise, mid-rise, and low-rise. Then, a lightweight low-rise, which represents hard-packed mixed single-story building with few or almost no trees. Large low-rise represents spread-out arrangement of buildings of 1 to 3 stories with few or no trees. The class of sparsely built represents sparse arrangement of small or medium-sized building in a natural setting, with abundance of plants and trees. The class of heavy industry is the mixture of industrial structures with few or no trees. The last 7 classes are conventional land cover classes including dense trees, scattered trees, bush and scrub, low plants, bare rock of paved surface, bare soil or sand, and water. This table shows the criteria that are used to define different local climate zone classes. They include the following: sky view factor, aspect ratio, building surface fraction, impervious surface fraction, pervious surface fraction, height of roughness elements, and terrain roughness. Now we will go through their definition one by one. Sky view factors calculates the ratio of the amount of sky hemisphere visible from ground level to that of an unobstructed hemisphere. Aspect ratio refers to the mean height to width ratio of street canyons. That is used for classes 1 to 7. Building spacing. That is used for classes 8 to 10. And tree spacing, used for classes A to G. Building surface fraction is the ratio of building plan area to total plan area in percentage. Impervious surface fraction is the ratio of impervious plan area, such as paved surfaces and rock, to total plant area in percentage. Pervious surface fraction is the ratio of pervious plant area, such as bare soil, vegetation, water, to that of total plant area in percentage. Height of roughness elements is the geometric average of building heights, that is for classes 1 to 10, and tree or plant height for classes A to F. Effective terrain roughness for city and country landscapes uses the definition described in Davenport's paper in the year 2000. This figure shows the multi-date temperature comparison among different local climate zones classes. It is a case study of Vancouver, Canada. The measurement was taken in March 2010. At the top of the figure, we can see the first 3 classes that describe urban landscapes, including compact high-rise, open high-rise, and large low-rise. Then the following 5 classes represent land cover in the suburban and countryside. The temperature measurements show significant differentiation between the urban classes and the non-urban classes. In addition, it also shows how urban morphology has helped to create urban heat island. As we can see, the temperatures for the compact high-rise are significantly higher than open high-rise and large low-rise. Here, we would like to show an example of local climate zones classification of Brussels. There are a couple of open source papers using Belgian cities as examples. The link to the paper is provided. We use the local climate zone generator to produce the map. The open source generator has a video to teach us how to delineate training areas from the study area. The left figure shows the training polygons for different local climate zone classes overlaying on Google Earth image. The right figure shows the classification map of Brussels. Once the map is created, it can be easily displayed on Google Earth for comparison and verification. We can merge this local climate zone map with the land surface temperature map from Practical 1. To do this, we will use the zone statistics in QGIS. To the left, we see the overlapping image of the land surface temperature generated from Practical 1 and the local climate zone classification map. To the right is the zoom-in of the overlapping images. After they are displayed in QGIS layers, we can extract the statistics of the surface temperature from each of the local climate zone classes. The table lists the minimum, maximum, mean, standard deviation, and majority of each class. The figure to the right is the plot for all classes. We observe the higher surface temperatures for urban classes as compared to natural landscape or vegetation classes. There is no real high-rise area in Brussels. We can see that the class of large low-rise, which has a few or no trees, and mostly paved, generated the highest temperatures among all classes. In Practical 2, you will practice the use of online local climate zone toolbox to generate a classification map, and repeat the exercise as shown here.